Hello world! My name is Kevin Dick, and I'm a PhD candidate in the Department of Systems and Computer Engineering at Carleton University in Ottawa, Canada. I'm eager to present our work entitled Machine Learning Pedagogy to Support the Research Community. Both myself and my fellow co-author and co-teaching assistant Daniel Kairolos are members of CUBIC, the Carleton University Biomedical Informatics Collaboratory, under the direction of our research supervisor, Dr. James Green. We are a collaboratory that focuses our research on the application of machine learning to diverse challenges in the field of bioinformatics, biomedical engineering, computer vision, and generally beneath the umbrella field of biomedical informatics. In this presentation, we describe our novel curriculum design to introduce undergraduate students to applied research through a series of course assignments and a competition amongst peers to inspire other educators. We describe the overall course structure and detail how the assignments were tailored to a selected open research question while developing student understanding of machine learning. For the selected COVID-19 related course-long problem of predicting which drugs might interact with specific proteins, we leveraged state-of-the-art tools for representing drug and protein sequences. We challenge students to develop unique solutions competitive with the current state-of-the-art models using reproducible notebooks and cloud-based computing resources, with the expectation that top-ranking solutions would be used to predict novel, druggable targets within the SARS-CoV-2 proteome to possibly treat COVID-19 patients. Excitingly, our experience ultimately resulted in the top student solutions being combined using a stacked classifier to create a publishable solution representing an actual research contribution. We highly recommend introducing undergraduate students to open research applications early in their program to encourage them to consider pursuing a career in research. Offered for the second time in the fall semester of 2020, an elective course entitled Introduction to Machine Learning under course code CISC 4996 was offered as an elective course to upper undergraduate students within the Systems and Computer Engineering department at Carleton University. The course was offered to 68 enrolled students in several engineering disciplines, including software, computer systems, communications, and biomedical and electrical engineering. The course assumed a number of prerequisites, including an undergraduate level of probability and statistics and knowledge of at least one programming language. The Python programming language was used throughout the course, however, experience in programming was quite diverse. Software engineers were clearly the most prepared at one end of the spectrum, and with biomedical engineers at the other having only an introductory programming course in their program. To assist all students equally, each of the weekly tutorials covered coding examples, implementing or demonstrating materials covered that week in the lectures. Also, accompanying each of the three assignments were skeleton notebooks within which students implemented their solutions and which greatly facilitated the benchmark evaluation of their work. This figure presents a conceptual overview of the course design and deliverables. The course is partitioned into three phases aligned with three assignment-type deliverables. As part of Assignment 1, or A1, the students are taught and evaluated upon machine learning foundations. In Assignment 2, the students form N groups and are introduced to the selected open research questions and evaluated based on their ability to implement, train, and test a baseline model, allowing students to familiarize themselves with the programming framework. The students are also asked to provide an overview of their anticipated approach to their final solution. In Assignment 3, students then implement, refine, release, and document their final solution. The top K of N selected solutions, using a systematically evaluated measurement to baseline and the state-of-the-art, are integrated into a meta-model using ensemble method and are re-evaluated against the state-of-the-art. Successful results warrant open source release and subsequent publication with contributing student authors sharing an equivalent contribution authorship. Excitingly, machine learning methods can be applied to a wide variety of domains given a suitable representation, whether they are manually engineered or learned through deep learning, and by abstracting domain-specific considerations of a problem into the type of formulation amenable to a given machine learning framework. For our course offering amid the pandemic, we selected the highly relevant problem of predicting whether specific therapeutics could be used to treat COVID-19 patients. The fully online learning environment and context of a global pandemic prior to vaccine availability made this problem particularly enticing to students and motivated the curriculum adaptation. Facilitating much of this coursework was the then recently developed Deep Purpose framework. Most excitingly, the project's lead developer, Kexin Huang, notes that among the embedding methods exposed through the Deep Purpose API, the vast majority of combinations of embeddings have yet to be exploited to evaluate their impact on DTI or drug target interaction prediction tasks, meaning that teams of students could each attempt a unique combination of embeddings and architectures as part of their individual solutions. The importance of such a framework cannot be understated. A critical component of this curriculum design necessitates a robust library developed by a domain expert or by the TA to abstract much of the low-level concepts into a numerical representation easily integrable in other machine learning frameworks. In leveraging this framework and providing minimum viable working solutions, students had access to a robust framework within which they could easily embed DTI pairs and feed them into the machine learning architecture of their choosing, for example Keras, PyTorch, Hugging Face, etc. The ability to train machine learning models and explore their associated hyperparameter space is often limited by available compute resources. To provide all students with an equal platform on which to innovate, Google Colab was used by all students for modeling and evaluation. This free cloud-based system provides standard development environments to all participating students. The democratization of such cloud-based hardware enables students in low computational resource environments to contribute to research initiatives in ways that they might not otherwise be able to. This platform also simplifies students' efforts to quickly get up to speed with a suitable development environment, complete with free GPU-accelerated compute resources. While ambitious, we expected that framing the assignment as a competition amongst their peers and to surpass a baseline set by one of the current published state-of-the-art methods would foster creativity and generate interest in research applications. Moreover, the suggestion that the work produced within the context of the course might eventually contribute to alleviating the COVID-19 pandemic and potentially save lives further motivated our students. The DTI predictors generated by students could be applied to predict candidate drugs that might be effective in treating COVID-19 patients. Emphasis on reproducibility ensured that resulting models could be leveraged by the community well beyond student coursework. Experientially, we gleaned several lessons from this work and summarized them here to support educators seeking to follow from our efforts. Lesson 1. Research experience inspires research interest. Anecdotally, following this course, some students considered pursuing research for the first time. Run in the fall of the terminal year of their program, this experience was offered at a late stage and would be more effective in the penultimate program year prior to students settling on a career in industry. From this experience, students realized that given a suitable library and cloud resources, they could contribute to interdisciplinary challenges with relative ease. Lesson 2. Focus on an interesting, well-formulated, and abstracted problem. The reality of the ongoing COVID-19 pandemic galvanized interest in biology-related problems related to the pandemic. However, students have a specific information technology or electric and computer engineering background, in contrast to a generalized interdisciplinary background. The use of the Deep Purpose API was key to generate effective data representations to permit non-biology students to contribute to a biology-focused challenge. Experientially, the generation of a reusable library or framework by a TA is itself a highly rewarding research contribution. Lesson 3. Provide a baseline and encourage creativity. Providing students with a baseline working model permits everyone to succeed. While some students will aim for a minimum viable solution, likely due to other commitments or limited capabilities, they should have a positive experience. Complementarily, the high achievers should be encouraged and enabled to go well beyond the baseline solution. By setting the baseline solution as one of the current state-of-the-art models to build upon and compare themselves, students are provided with a tangible and empowering sense that they can advance the frontier of knowledge. And finally, tempering performance expectations. While not a lesson per se, a final note on running a student-centric competition as part of machine learning pedagogy is to temper one's expectations of the outcomes. While research advances have been achieved through competitive environments, such as the effect of the Kaggle Live leaderboard that encourages continual innovation beyond the best practice, it should not be assumed that framing a student-centric research competition will necessarily yield noteworthy results. In conclusion, upper undergraduate pedagogy represents a unique opportunity to introduce students to the research community and excite them with the potential to generate actual research contributions by leveraging their creativity in generating notable solutions. Machine learning course educators, as with their students, are expected to benefit from the experience of tailoring machine learning projects to relevant applied research projects. We encourage machine learning educators everywhere to follow from our example and incorporate applied research projects within their curriculum design. Thank you all for your interest in our work.